Okay, good day class. So as requested, I'm going to have this recorded review lecture on unit operations. This is actually divided into three parts, and I will start with the first part this afternoon, which covers the topic on evaporation, heat exchangers, crystallization, and drying. So when we speak of evaporation, it's a special case of heat transfer to a boiling liquid. The intent or the objective is to concentrate a non-volatile solute from a solvent, which is most of the time water. Now this is done by vaporizing or boiling off the solvent, and as such a concentrated product is obtained. Now concentration by evaporation is normally stopped before the solid begins to precipitate, because in that case it will now be under the unit operation process, which is crystallization. Now evaporation is usually treated as the separation of a liquid mixture in a liquid product we refer to as the concentrate or the thick liquor, and the vapor byproduct. Though in some instances, in the case of water treatment and desalination, the vapor, which is in most of the time considered as a byproduct, is now the main product, and the thickened liquor, which contains the contaminants, is considered to be the byproduct. So it really is depending on the objective of the evaporation as to how we classify the byproduct as the main product. Now this is the schematic of a single effect evaporator used in single effect evaporation. You have this as the heating tube, or we call the steam as the heating medium. You have this as the vapor space on top, and in here you have the calandria tubes. Now the feed in our schematic should be labeled as F, the vapor should be labeled as V, the steam should be labeled as S, and the condensate or the drips labeled as the C. The thickened liquor is labeled as L. The temperatures are having the subscripts of F, S, depending on what it represents. So F is for the feed and S is for the steam. The speed that you see written on the vapor space is the operating pressure of our evaporator. And this is the pressure we used in finding the saturation temperature of most of the time steam, which is water turned into vapor. Now, how do we measure the performance of our evaporator? So there are three ways of expressing the performance of our evaporator. One is in terms of its capacity, the amount of vapor that it produces per unit time. Second is economy, how much vapor is produced per kilogram of steam used. So that's economy. As to steam consumption, it's the combination of these two. So we get the steam consumption by dividing the capacity by the economy. So any of these three could be considered as the performance measure of an evaporator. Now there is this thing what we call boiling point elevation. Now it's a concept wherein as more and more solute remains in solution, or as more and more water is vaporized, the boiling point of our solution increases. It's because of the increase in the solid content of our solution. How do we quantify this increase in the boiling point? We quantify it using DUHRING'S rule. Now, the main challenge in DUHRING'S rule is that we have to know where it is located in our handbook. You have to look at the diagram, and you have to use the appropriate data. That way, you'll be able to determine the boiling point of your solution in that diagram. If you know already the boiling point of the solution, the boiling point elevation or the boiling point rise is simply the difference between the boiling point of the solution minus the saturation temperature at the indicated operating pressure of your evaporator. So in your handbook, if you're using the 8th edition, DUHRING'S chart is in figure 11-124. Now, in the case of dilute solutions, those solutions that contain less than 10% solids or solutions of organic colloids, we may neglect boiling point rise or boiling point elevation. But if the problem is silent, that we are to assume that we have boiling point rise negligible, we are not allowed to do so unless that we have concentration less than 10%. Now, the DUHRING'S chart is comparable to this, but this one is the very simple version of the DUHRING'S chart, and you have also seen it in your unit operations book. However, the system that you have there is simply NaOH and water, or sodium hydroxide and water. Now, in this particular chart or graph, you have on the x-axis the saturation boiling point of water based on the operating pressure of your evaporator, and on the vertical axis you have now the boiling point of the solution. How do you get the boiling point of the solution? Is you make use of the saturation boiling point of water at the pressure indicated in your problem, and then the percentage by weight of your solid in your feed and inside of your evaporator, rather not in the feed but rather inside your evaporator. Once you have the concentration of the solid and the saturation temperature of water, you just simply project it on the left and you have already the boiling point of your solution. So boiling point elevation is just the difference of the boiling point of the solution and the boiling point of water. Now, there is a simple formula that I was able to get out of my readings in determining the boiling point elevation when water is the solvent. So, in this formula, you only need the mole fraction of water. So, take note, it's mole fraction, it's not mass fraction. So, if the problem provides you with mass, you have to convert it to mole fraction. So, mole fraction of water, latent heat of vaporization of water at 180 atm pressure would be this. If it's not 180 atm pressure, you go back to the steam tables and get the corresponding saturation pressure at the saturation temperature at that given pressure if it's not 180 atm. And also, you can get from that particular steam tables the saturated vapor enthalpy and the saturated liquid enthalpy at the indicated pressure. So even if it's not 180 atm, you can still determine this latent heat of vaporization. You just simply use your steam tables. So with this, you have also to use the universal gas constant, and if you're dealing with SI units, you use this 8.314 joule per mole Kelvin value. Your T prime is the main objective, and that is the boiling point of the solution. Your T is the saturation boiling point of water at the indicated pressure again. So if you know already T prime, then you'll be able to get the delta T sub B. So again, if your problem gives you the mass, you need the molecular weights of your water, and so that you'll be able to convert the percentage by mass to percentage by mass to percentage by mole. Now, if you're going to go back to Chem 1, we have this particular boiling point elevation of solutions whenever the solid dissolved in it increases in value. So it has a corresponding effect on the boiling point of such solution. And it could be determined using this fundamental basic formula from chemistry. And then this was also discussed in your physical chemistry. So in here, you'll be using the molar boiling point constant of the solvent. So I like this formula because it's not limiting. The solvent need not be water. It could be any solvent. All you have to do is find this molar boiling point constant. However, again, in this case, you're not using mole fraction or mass fraction, but this time you're using molality, and that is number moles of solute per kilogram of solvent, which is water in this case. So number of moles of solute per kilogram of water, that's for the molality. then you'll be able to get the delta T sub B. This delta T sub B, if you will add to the boiling point of water based on the saturation temperature or pressure, then that would be now the boiling point of your solution. The boiling point, the original boiling point, will rise or will increase based on this computed delta B. Now, I have also encountered in my readings that this K sub B, the molar boiling point constant, is also known as the ebullioscopic constant. So, just in case you will encounter this, so they just mean the same thing, the two. Now, as to the material balance for a single effect evaporator, the feed is equal to the amount of liquor produced plus the water that was vaporized from the feed. So these two should be equal, and patterned after the overall material balance will be the solute balance, wherein you will simply multiply the F and the L by the weight fraction of the feed and the liquor respectively, depending on what the problem provides. So if the feed, the L, and the V are in terms of mass, so this should be in terms of mass. If this is in terms of mole, this should be in terms of mole. You just have to simply make your units agree. Now, there's no V term on the right side of the equation for the solute balance because we always assume that there is no entrainment, meaning no solid was carried by your vapor as it leaves the evaporator. Now, there are cases wherein there is entrainment, but this could be assumed very, very small compared to the value of the entire amount of vapor that leaves the column. So, as such, your YV, that's the mole fraction of the solute that is entrained in your vapor, is assumed to be more or less equal to 0, even if there is a case of entrainment. This is for our material balance. You have the overall material balance and you have the solute balance, or simply called the solid balance. Now, we have also the energy balance equation, because if we will be asked what is the amount of heat transferred to and from the feed, then we will have to use this particular energy balance equation. You will simply account for the total energies of the streams that enter your evaporator and the total energies of the streams that leave your evaporator. So you will be needing here the enthalpies, and these enthalpies, the HF and the HL, could be taken from the enthalpy concentration diagram. You have seen equivalence of this in your textbooks, and even there is one in the handbook. Your textbook is only limited for the system, NaOH, and water. So please check in your handbook what is available in terms of the enthalpies. Now, this lambda S will be taken from the steam tables because this is the latent heat of vaporization of the steam. As to the vapor, it depends. This could be the saturated enthalpy of the vapor, or this would be the saturated enthalpy of the vapor plus the superheat. We call it the superheat if we have a case of the boiling point rise or boiling point elevation. Now, this is again our evaporator, and I have already placed in here the corresponding variables that could be given together with the stream. So you have the steam. This is S in our books. This is F in our books, and the CP of the feed may be given, so as we can account for its enthalpy should the feed be of a composition of a solute that is of unknown identity. So based on the CP, we can still determine its energy content, and that's its enthalpy. Now, this one is condensate, so this is C in our books in terms of representation. This vapor is V, and we have the thick liquor as L. In here, it's MP, denoting P for the product. Most of the time, it's the thick liquor that is the product. So the energy equation or energy balance equation you're seeing here is actually now this one. This is now your energy balance specifically, or the enthalpy balance. we have isolated on the left side the amount of heat that steam has to provide or give off in the calandria of our evaporator. That way, the amount of vapor that will be vaporized so as to concentrate our feed will be achieved. Now, in terms of determining the heat transfer, if provided with the overall heat transfer coefficient of each of our effects in the case of multiple effect evaporation or of our single effect evaporator, this would be the equation. This is actually the heat transfer equation that was discussed in your momentum transfer in convective heat transfer. So you have UA delta T, where your delta T is the difference in the temperature of the steam and the boiling point of your solution. So area is of course the area, the heat transfer area of all the tubes summed up in your evaporator. Now, the heat supplied by the steam is actually in formula Ms lambda S. We know this is standard, but this is same heat that your feed received. And in this is the same amount of heat that was translated into the formation of part of your feed, which is liquid, into vapor. So what you could see here in the formula on top, it's the sensible heat, okay, of your feed, F for the feed, and the latent heat of vaporization in the case of your vapor. So this is the boiling point of your feed, or the boiling point temperature, the saturation temperature of your feed, and this one is your feed temperature. In some cases, this is the temperature of the feed minus some common or only two common base temperature. And what is that base temperature? The base temperature is 32 degrees Fahrenheit. If it is in English, it's 25 degrees Fahrenheit. Or rather, is it 0 degrees Fahrenheit rather, not 25. It's 0 degrees Fahrenheit if it's in 0 degrees Celsius if it's in SI. 32 for English, 0 for SI. Fahrenheit for English, Celsius for SI. So if you use that, you can use the lambda V here. But if you use the boiling point, the saturation boiling point, based on the operating pressure of the vapor space minus the temperature of the feed as indicated, this lambda V is not lambda V, but rather this is really the enthalpy of the saturated vapor. Please recall and go to your notes as to the difference in using the two formulas. If this is lambda V, this F here is the base temperature, and this is the temperature of the feed. If this is the boiling point temperature of the solution in the indicated pressure of your evaporator, this is the temperature of the feed. This one is not lambda V, but rather this one is HV. I hope I made that clear, because the two formulas are equal whenever you just apply the correct temperatures here. The temperature difference that should be used in the sensible heat term in accounting for the heat supplied by the steam. Okay, so everything here is defined. Now, for the majority of the evaporation process, the rate of heat transfer is the controlling factor, or in design, it's really the governing factor, that is the rate of heat transfer. The rate of mass transfer only becomes secondary, and it only becomes important when we are producing a liquor which is very high in concentration. Okay, so if you will be asked what will be the controlling factor in the design of your evaporator, it's really the rate of heat transfer, not the rate of mass transfer, which actually is the main objective why we are having evaporation. We want to transfer mass from the feed into vapor, or convert it into vapor so as to concentrate the feed. So you have to take note of that. This is a sample problem which you can read, because anyway I pasted the solution. It's different than the way we solve it in class, so I selected this because so you will have a different take on evaporation, and this one is another one. Okay, so we can proceed with multiple effect evaporation. So the illustration here gives you a triple effect evaporation system. So the steam is introduced in the first effect and the feed is on the first effect, telling us that this is forward feed multiple effect evaporation. You have the condensate being removed in each effect, and then we have the liquor from the first effect introduced on the second, the liquor in the second introduced to the third, to produce a final product which is of higher concentration than the product that could have been withdrawn on the first effect. So the heating medium of the succeeding effects are the vapor coming from the previous effects. If the feed is introduced here on the last effect, that would be backward feed multiple effect evaporation. So please check your notes on that from heat and mass transfer, so that you will have something to reinforce here regarding the different modes of multiple effect evaporation. Now, aside from the material balance and the energy balance to consider in multiple effect evaporation, we have these three formulas also. But I'd like to go to the formula for single effect and discuss how we write the material balance and energy balance for a multiple effect evaporation system. So if it's an overall material balance for the entire system, the F is still of course the F. Your liquor will be the liquor taken from the last effect, and that's the final product liquor. The V will be total vapor evaporated from all effects. This is not the V of the last effect, but rather the V of all the effects. So when you do solute balance, the same thing with the multiple effect evaporation, you will only have solids to account in the feed and in the final liquor. So whatever is your effect number, or let's say you have a quadruple effect evaporator, this becomes L4XL4, denoting that your final product is being withdrawn from the last effect, that's the fourth effect. Now, in terms of energy balance class, it's not suggested that we do overall energy balance at the start when we have multiple effect evaporation. We only do that when we have already to determine the amount of heat supplied by the steam to provide the energy necessary to vaporize all the water that was vaporized in all effects. We can do that only after we have done the energy balance of each of the effects. So again, you are allowed to do overall material balance because you are required depending on what the problem is asking. But it should be done at the end when you have already finished the trial and error part of determining the areas of all your effects, which is class at all times assumed to be equal. We don't design a multiple effect evaporator system wherein the areas of the evaporators are not the same. So in this case, you do energy balance on each of your effects. This one, the energy of the feed plus the energy of the steam equal to L1HL1 plus V1HV1 when we speak of the first effect, energy balance, when we are considering the energy balance of the first effect. Okay, for the second effect, then your feed will be your L1 and your heating medium will be the V1, because your heating medium in the second effect is your vapor from the first effect. Then your product there will be L2 and your vapor byproduct is V2, and so on and so forth. So you do energy balance first on each of your effects before you do the overall energy balance for the entire system that you are given. So we go back now to where we are. So aside from those formulas, you have this for multiple effect evaporation. We need to get the summation of delta T, which is the temperature of the steam minus the temperature of the last effect minus the summation of BPRs. The BPRs would be the boiling point rise of each of your effects added. So you have to subtract it from the difference of these two, and that would be your overall driving force for your system. Now this summation of delta T will be used in determining the delta T of each of your effects. So in this case, class, you will be using the overall heat transfer coefficient of all your effects. Now the numerator overall coefficient of heat transfer will be based on what particular effect are you determining the delta T. So if this is delta T1, then you will have 1 over U1 in the numerator. The summation of delta T that you got here will be substituted here. This will be true for all the delta T's that you will determine, so that you'll be able to construct your temperature distribution diagram that was discussed to you in HMT. So again, review your notes on the temperature distribution diagram. Why the need for the delta T's? You need the delta T's for you to be able to determine what is really the boiling point of your solution. You cannot determine the enthalpies of your vapor unless you know the temperature of the vapor space, and that is based upon the temperature from the delta T that you solved in here. The delta T that you solve in here is the difference in the temperature of the heating medium minus the temperature of the vapor space in that particular effect. Again, the delta T of a particular effect is equal to the temperature of the heating medium, so it could be the steam or it could be the vapor of the previous effect, and the temperature of the boiling of your vapor space, or that's the boiling point temperature of your solution. I'm saying the boiling point temperature of your solution because you will use now the elevated boiling point temperature if it has a R. So that's why you need to get the delta T. Now, what if in the last part wherein you already solve for the areas, I will give you a formula in determining the areas that you got for your effects are not really more or less the same or equal. There's a need for you in that case to have this correction in the delta T's for your effects, and that will be the delta T sub x prime, and that is solved using this. It would need the original delta T, the area of that particular effect, and the mean of the areas of all your effects. So the mean is simply the average of all the areas that you have determined for your particular multiple effect evaporation system. Now, corrected temperature of effect X should A's vary by more than 10% from A sub M. So we do this whenever our areas vary by more than 10% from each other's value. If they don't vary that much, then it's okay. What we use as the area of each of the effects in our multiple effect evaporation system is the mean. So if you would be asked in the problem, what is the area of the effects, that would be the mean of those areas which are not equal. You are allowed to answer that as long as the difference in each of the values are not more than 10%. Now, and speaking of area, how do we determine this area, each of the areas? That would be determined using this particular concept. We assume, though it's not correct, but we assume for simplicity purposes that the amount of heat transferred in each effect are all equal. So if that is the case, if our effects should be identical, the A's will cancel each out, and we have this particular equation. Okay, and we have already the delta T's. If not, if we cannot use this particular formula because anyway we have assumed that the A's are equal, what particular formula will be used so that we'll be able to get the A? That would be the basic formula of Q being equal to U A1 or U A delta T. From the amount of heat transferred, for example, in the first effect, which is just the amount of heat supplied by the steam, you can already determine A1. again, from Q1 of the first effect, which is equal to the S lambda S. You can check your notes on that. Then you can solve already for A1 because that heat is equal to U1 A1 delta T1. So if you know already A1 and you will not assume outrightly that these A's are equal, then if you will equate these two, you will get A2. If you have A3, if you equate naman A3 to this, any of these two, you will get A3. So if you have a triple effect, for example, you already know A1, then you just equate U1 A1 delta T1 to U3 A3 delta T3. That will help you solve for A3. Same thing that you have used this formula here. The A's that you should be getting should not vary by more than 10%. So if they don't vary, then hallelujah, you can solve for whatever are the next questions in the problem for multiple effect evaporation. If not, you have to redo everything by correcting your delta T's using this particular formula. That's in the case of multiple effect evaporation. Now, the reason why we do multiple effect evaporation is we want to capitalize or really exert or use up all the energies that our steam gave, so that our vapor will be produced from the water or from the solvent that is from the feed, so as to concentrate the feed. So in this case, there are other methods, new technologies that are being used. That way, this particular basic way of using up or capitalizing on the latent heat energy of the steam could be improved. And that is the case of thermal vapor recompression and mechanical vapor recompression. So for thermal vapor recompression, this uses a steam ejector to compress the vapor leaving the evaporator vessel. In this application, the steam ejector is often called a thermocompressor. Its primary purpose is to compress the vapor, but its secondary benefit is to create vacuum within the evaporator vessel. As a thermocompressor, the ejector uses high-pressure steam as the motive fluid to draw in the low-pressure vapor from the evaporator and produce a combined vapor of suitable pressure and temperature for evaporator heating. If I will simplify this class, one of the main purpose of the TVR or the thermocompressor in compressing the vapor before it's introduced on the next effect is really providing or creating a vacuum inside your system. If it's creating a vacuum inside your system, your fluid inside your evaporator will, of course, be boiling at a much lesser temperature. If it's going to boil at a much lesser temperature, the difference between the temperature of the steam and the temperature of the fluid that boiled at a much lesser temperature because the evaporator is under vacuum will be higher. So based on the formula, your delta T will increase because your T sub B, the boiling point of your solution, decreased. So that's the main objective of really using the thermocompressor. Aside from increasing the latent heat of the vapor that will be used in the successive effects, it also creates a vacuum inside the system. So creating a vacuum increases the amount of heat that is transferred. Now, what about mechanical vapor recompression on the MVR? Now, uses on the other hand a mechanical compressor. If this one uses thermocompressor, this one is a mechanical compressor or fan to compress low pressure vapor leaving an evaporator to a higher pressure and temperature to reuse as the evaporation heat source. The internal reuse of the vapor also eliminates the need for an external condenser, which most evaporator systems need to condense the vapor leaving the last effect. So in this case, class, the beauty of using the MVR is that there's no need for you to have a condenser on the last effect, because the vapor that gives the last effect is now in itself already more or less in the near condensing form, if not in the condensed form already. That's in the case of the MVR. So this is a schematic on how a thermocompressor works for a multiple effect evaporation system. So you have the vapor from this effect introduced into this thermocompressor before it is introduced on the next effect as a heating medium. Now, it's really fundamental in the understanding for multiple effect evaporation class that the boiling point on each effect decreases. So if you notice, the boiling point of your solution as we go from one effect to another decreases. Okay, in the case of multiple effect evaporation, it's because the pressure also decreases. Now, this is for your mechanical vapor recompression on the other hand. Now, I got this from my readings on how do we compare the savings measured in terms of steam economy for a single effect evaporator and for a multiple effect evaporation system, and for a multiple effect evaporation system with TVR and MVR. And notice that a single effect compared to a single effect with MVR will have very great disparity in steam economy. So with just 1 kilo of steam used, this one can vaporize 10 kilos to 30 kilos of water. Take note. While this one, for every kilo of steam used, only 0.9 kilograms of water is vaporized. Single effect. We increase that in terms of, we increase the savings when we increase the number of effects. And as such, we have already a system in that case, or a multiple effect evaporation system. And it is this much that we have in terms of steam economy. For triple effect with TVR, a regular triple effect will have this for the steam economy. A triple effect with TVR will have 4 to 8. So that's really big savings in terms of the costing, the cost of steam. You have made use of the of the amount that was spent for the steam, because the amount of water that was vaporized is increased. So this is worth noting just in case you would be asked in a form of a statement as to steam economies. Now, for solve problems in multiple effect evaporation, I have inserted it here. So this would be also given in the form of a file just in case you won't be able to view the inserted file. So study this so that this could also, together with your notes in HMT 10, would help you process the problem set on the topic of multiple effect evaporation. Okay, so if we go back to our slide, I think that would be the last in here, the problems on multiple effect evaporation. And our next topic would be the heat exchangers. So we'll have a break and we will have heat exchangers after this.